Hello students, in the last class we have seen several basic terminology of tree and we understood what is tree and why we should use tree and what is the difference between tree and some other data structure like a linked list and array list, something like that. We have seen several categories of tree. We have seen binary tree and we have seen several type of binary tree and we have seen what is general tree. So binary is most important tree data structures. So you probably need to use this binary uh, in your in following courses, and probably if you are going to be a programmer or engineer, probably to have you need to do a lot of coding in binary using binary data structures. So today we'll start with the implementation of a binary. We'll see that how we can implement a binary tree. We'll see some methods of accessing binary tree. Then we will move to some other tree data structures. So just uh, just recap a little bit. A binary What is binary tree? A binary tree is a tree that that satisfies certain conditions. So if tree is empty, then you can call them a binary tree. If tree is not empty, then every node of that tree has at most two children. So it might have zero children, it might have one children, it might have two children, but it never have more than two children. So if it satisfies these conditions in a tree, then you can call them a binary tree. Let's go to the terminal and to understand how we can implement a binary tree. So here we have uh, programs a class called binary tree, and binary tree takes some e-type data. That means that e basically depends on what type of data you want to keep in the tree. If you want to keep integers, then e should be integer. If you want to keep float, it would be float. If you want to keep string, then it will be string. Then we implement some interface. That interface coming from the Java library that calls serializable. That serializable used to handles some uh, some taking some user input and inserting that input into the binary tree. So this is not that much important serializable. We basically focus on how to build a binary, the real concept, the actual concept, actual basic things of the binary. So we have seen that binary tree maintains several nodes like in linked list. So when we implemented linked list, we had to have some node class to create some node, and we use that node class to create object, to create node, and after creating node, then we can add those node to a linked list. We have seen those things when we implemented linked list. So similarly, a binary tree or a tree has several nodes, so we must have some node class to create those nodes. So that's why we have a inner class. That class is node, and that also implements serializable. And these are three members. So in single linked list, we have seen that a node has two members. One is for data, and one is for forwarding node address. And we have seen in the double linked list that the double linked list might have three different members. One is for data, and another one is for second one is for forwarding node address, and third one is for previous node address. So here, since tree node doesn't need backward node informations, but it might have several nodes. But we are talking about the binary node, so binary node at most have two forwarding nodes, or two successors. That's why we have total three members. One is for data and another two is for two successors. So one successor is called left, another successor is called right. Left tree and right tree. So these are the three members of a node. So this member keeps data and this member keep address of left children, and this node keep the address of right children. So now you have the constructor. You can have two different constructors. The first constructor take a data, and this data will keep into the node, and left tree and right tree will be null by initially. And we might have some two-string method. That two-string method are coming from Java library, and we, in order to print data of the tree of the node, so we just use the two-string method. Okay, so in linked list we have seen that we create some head node, so head of the linked list, and by default that head was null. Then we change when we delete head, then we change the head informations, is something like that. And tree also, we don't have head node but we have root. So initially no root is null, so that's why we create a node called root. That basically root is a node type variables, and it contains the information of the root of the tree. Then we can create binary tree by calling the constructor in a three different way. The first one is we are not passing any data information, so root would be null. So using this constructor, we create a tree. That tree is empty, so it doesn't have any node. So root is null, so the binary tree is empty. So another way we can construct a binary tree, that is we pass a root node, and that root node will be assigned to this root. So we have a binary tree that has only root. Now third way to create a binary tree, we pass a root data that we want to keep in the node, and we pass a left subtree and we pass a right subtree. So both are the binary tree type informations, so left tree and right tree. So using these informations we can create a binary tree. So data will be in the root node, and then we attach this left tree and right tree with the root. So if left tree is not null, the information that we are getting into the constructor, if left tree is not null, then root dot left will be assigned by left tree dot root. So root of the left tree will be connected to the root dot left. That means the left child of the root will be assigned by left tree dot root, the root of the left tree. And if left tree is null, then root dot left should be null, because there is no any information of the left tree. So similarly for the right tree also, right tree is not null, then root dot right. So root dot right will be assigned by the right tree dot root. That means right child of the root will be assigned by the root of the right tree that we are getting through the constructor. And finally, if root tree is null, then root dot right should be, right tree is a null, then the root dot right should be assigned by null. So this is a three different way constructor that we can create a binary tree. If we are not getting any information for creating a binary tree, then binary tree will be empty. If we get only root informations, then we will create a binary tree with the root informations only, and right child and left child will be null. And if we get root data plus left tree information and right tree information, then we create a root, and in the left child of the root we connect the left tree, and in the right child of the root we connect to the right tree. Then we can have several methods. So to implement binary tree. So for example, if you want to get a left subtree of the tree, so then you can create a method called get left subtree, and that basically return a binary tree. That basically return a tree which is a binary tree. So return type is binary tree. So get left subtree saying that if root is not null and root dot left is not null, so because we are getting left subtree, so it should not be null. So root dot left is not null and root is not null, then it returns binary tree root dot left. So that means it returns the left portions of the binary tree, root child, left child of the root. It returns the root child, left child of the root. That is a binary tree. If root is a null or root left is a null, then it returns null. So this is the idea of how to get left subtree. So that means that if you go to the file again, for example, this is your tree and this is your root. And if you want to get a left tree, so left tree is a left subtree is these portions. So how do you get this left subtree? So you can get left subtree. This is a connection with a left child of the root to the root of this left subtree. So that basically saying that, so if root is not null, so root is not null because we have some informations. Then saying that root left not equal to null, so root left child is not null because it has some left child over there. So then it returns root dot left. So it returns address of this node. It returns root dot left means it address contents of left child of this root. So that means address of this node. So this is basically take the whole information. So by accessing this node, you can access all these nodes. So that basically saying that how to get the get left subtree. Similarly, if you want to get left right subtree, so get right subtree, so you have to check that if root is not null and root dot right is not null, then get the root right. So if you go to the file, say you want to get this right subtree, you check that root is not null and root dot right is not null, so this is not null, so it returns root dot right. Root dot right basically return the address of this node, and if you return this address of this node, then you can access this other node also, because these are the linked list concept. So this has the forwarding node information, so you can access all of them by accessing one by one. So this is the way how to get left subtree and how to get right subtree from the binary tree. Now, how to check that whether a node is a node is a leaf or not? How to check that one? So for example, so there is a boolean functions that returns true or false. If node is a leaf, then it returns true, otherwise it returns false. So how do you check that? If root dot left equal to null and root dot right equal to null, that means that node doesn't have any left child, doesn't have any right child. So we know that if a node doesn't have any child, it doesn't have any left child or any right child, then we can call them a leaf. Similarly, we are checking that if root dot left is null and root dot right is null, then we can say that that node is a leaf. So in that case, it returns true, and we can say that this node is a leaf. Now you have some supporting method. This is not a basic method to binary tree. So this is toString method. That toString method basically print all the data of the binary tree. So you must have some for loop, and you run this for loop until up to the depth of the tree, and every time you basically print some informations and you append some string. It's just and you call this toString method recursively. You can see that toString method, you go to the left node and you increase the depth, and you print some informations in this node. So this is some method to printing information. I'm not going to explain this toString method. You should read this method to understand everything. So it's not, it's just how to print informations from the binary tree. And this is also how to get information, some user input, and assign to the binary tree. So probably you want to create some binary tree before accessing. You want to insert data into the binary tree, and this is the way how to insert the data binary tree. So you read some data from the using some scanner class, and you stream that data, just eliminate all the extra spaces, and you get some data. And if data is not null, then you assign those data into left tree and into right tree, and you recursively call this binary tree, and you know read binary tree. You recursively call this read binary tree, and insert that data into the tree. So this is the how you create a binary tree. So you might have some constructor, you might have three different members, and you can get some get subtree and left subtree, and you can create that binary tree using string build. You can use some functions called read binary tree, getting some scanner input, and using that input you just call you just create the binary tree functions, binary tree data structures. So these are some implementations of a binary tree. And now today we'll see some another variation of a binary tree that calls binary search tree. So binary search tree is a binary tree, but it has some more restrictions. So here it's saying that if T is empty, then you can call them, this is a binary search tree. So exactly what we have seen in our previous slides, our previous lectures, that if T is empty, then you can call them a binary tree. Here you can also call them a binary search tree if T is empty. If T is not empty, its root node has two subtree, TL and TR, such that TL and TR are binary search tree. The value is the root node of T is greater than all value in TL and is less than all value of TR. That basically saying that if value of root node greater than all value of the left subtree and value of root node less than all value of right subtree, then you can call them a binary search tree. So that means every node in that binary search tree should satisfy these conditions. Every node has, you know, uh, lower value in the left subtree. Every node has greater value in the right subtree. So if you go to, if you see some, let's see some examples. So for examples, if you go to these, these things, so the whether this one is a binary search tree or not. For examples, if you, uh, so say for example, so you have 23 over here. So you have 23 over here. 23 is bigger, so you have 23 over here, and you have, say, you have, say, 20, no, 19. Oh yeah, this one. Okay, this one. So then you have, So you have, say for example, this is 19, and this is, so this is, say 12, and this is, say 9, and this is, say for example, 21. Now you can see that every node, the value of every node is greater than of their all value of the left subtree. So if you compare this one, this node has 23. So all the value of left subtree is smaller than this 23. So you can see the 9, 12, 19, and 21. All value in the left subtree of this node are lower than this value. Now if you compare this one, you can see that all value of the left subtree of this node are lower than this one. 9, 12 is lower than 19. So so you compare this one, so all value of the left subtree is lower than this one. Now what about this one? So now let's add some more informations. So you have 33, you have 54, you have 20, 29. Okay, now if you consider the right subtree, so all the value of the right subtree is greater than the value of the root node. So you can see that this is the 23, and all the values of the right subtree is greater than 23. 33, 29, and 54, all values are greater than 23. And if you consider this one and this one also, all the values in the right subtree is greater than this one, all the values of left subtree is lower than this one. If you consider 19, all the values of left subtree is lower than this one, all the values of right subtree is greater than this one. So you can see that all the nodes satisfy these conditions. So the condition is that each node will have the value that would be greater than all values of the left subtree, and that would be lower than the values of right subtree. If you satisfy these conditions, then you can call them, this is a binary search tree. A binary search tree is a binary tree and it must satisfy these conditions. Then you can call them a binary search tree. So go to the slides again. So this is our formal definitions. So if T is empty, then you can call them a binary search tree. If T is not empty, then its root node has two subtree. Obviously, it's two subtree because it's a binary tree. So TL and TR, such that TL and TR are also binary tree because TL and TR also satisfy the condition of the binary search tree. The value is the root node of T is greater than all value in TL, and it should be less than all value in TR. So that's that we have seen in our example. Then you can say that this is a binary search tree. So using the binary search tree, you can find some you can use you can find some value very easily. Say for examples, yeah, say for example, so you have a search algorithms and you want to find something from an array. So and you don't know index to find something from an array. So what you need to do, you need to traverse the whole array, and you probably need to check all the elements of the array to find, to find something. So say one by one you check, and probably you need big O and complexity to find something from an array. So if you consider linked list, and if you want to find something from the linked list, probably you need to visit all nodes of the linked list to find something. But in order to find something from binary search tree, you don't need, any you don't need uh, you don't need to visit all the nodes. Probably you need to visit probably half of the nodes, or lower than half of the nodes, or maybe some of the nodes to find something. So these are the algorithms. So for example, this is some recursive algorithm to in order to find something from the binary search tree. We'll see in an example. Say if tree is empty, then it returns null. Then that means a tree doesn't have any data. So you're not you didn't find anything from the tree. If tree is not empty, then if the target matches the root node's data, then you return the data. That means you found the data. If your target value is equal to the root node data, then you found the data. If it is not, then if the target is less than your root data, then you go to the left side of the tree. And if your target is greater than your root data, then you go to the right side tree. So let's go to the problem. Say for examples, you are looking for 29. So this is a 29 over here, so you are looking for root 29. So you start with the root and you check that 29 is not 20, so root data is not 29. So obviously you didn't find the 29. So you know that 29 is greater than 23. So since 29 is greater than your target value is greater than 23, you don't need to traverse the left portions, because you know that all the data in the left portion are smaller than 23, but your target value is greater than 23. So you don't need to traverse this portion. What you need to do, you just jump to the right portions. So you come this side, and after coming this side, you see that the value is 33. So your target value is 29 and the root value is 33. So since 29 is lower than the 33, so you don't need to jump to the right side. You have to jump to the left side, because right side have greater value than the root value. So you don't need to traverse the right side. So since 29 is lower than the 33, so you go to the left side. After coming to the left side, you check that 29, this root value is similar to the target value. So you found the data. So now did you see that how many comparison you have done to find 29? Only 1, 23, 33, and 29. Only three comparisons, only three iterations. You in a three iteration you found your data. So this is the benefit of having binary search tree. So if you have binary search tree and if you maintain data in binary search tree, then probably you don't need to traverse a lot of data. You don't need to check a lot of data, and probably you need very little amount of comparisons to find some data. So this is the benefit of having binary search tree. So when you have a lot of data, so probably you might keep data in the binary search tree, and probably if you want to find data very frequently, then probably you maintain data in binary search tree, and you can easily find those data. If you want to search something from the binary search tree, then probably you can find them very easily. The only restrictions of having binary search tree is that you have to maintain data in a sorted order. You can see that all the data in some orders. So you can see that all the data in the left subtree are smaller than the root node. All the right subtree values are greater than the root node. So this is the way how to maintain binary search tree. So in order to maintain binary search tree, you have to maintain some orders. So far this is a binary search tree we have seen. So we have seen binary tree, we have seen some various uh, various informations, various categories of binary tree, full binary tree, complete binary tree, and perfect binary tree. Now we have seen binary search tree. Now the the next one is the tree traversal. So if you want to traverse a tree, so you can traverse a tree in a different way. So there are three different ways to traverse a tree. Traverse a tree means you are printing data of each node, or you are applying some functions on each node, so you might need to traverse the whole tree. So there are three different ways to traverse a whole tree. There are three different ways to traverse a tree. So one is called pre-order, another one is called in order, another one is called post order. So pre-order says that visit root node, then traverse the left tree, then traverse the right tree. So and in order says that traverse the left tree first, then visit the root node, then traverse the right tree. And post order says that traverse the left tree first and traverse the right tree and then visit the root node. So you can see that in a three different traversing, you know, the order basically change the visiting root node. You see that always left traversing left tree comes before right tree. Left tree, right tree, left tree, right tree, left tree, right tree. But visiting node is visiting node root node is a different in a different traversal way. So pre-order basically saying that you are visiting root node before everything, that's why it's called pre-order. And in order basically saying that you are visiting root node in between left and right, that's why it's in order. And post order saying that you are visiting root node after traversing TL and TR. So the names pre-order, in order, post order basically representing the order of the traversing. So if you visit root node before everything, that is pre-order. If you are visiting root node in between left and right subtree, then it's in order. And if you are visiting root node after left and right tree, then it's a post order. Let's see one example that algorithms. So today we'll see some algorithms, then in next class we'll talk about some examples and implementations of these tree traversals. So if you are going to pre-order traversals, if tree is empty, then you just return. Okay, so if tree is not empty, so you follow these three steps. So this is a recursive steps. Visit the root node, since it's a pre-order, so you are visiting root node first. Then call the pre-order traverse functions with the left subtree, and call the pre-order traverse with the right subtree. So you can see that. So if it is a pre-order traversals, so you visit the root first, then you call the pre-order traverse function with the left subtree, then you call the pre-order traverse with the right subtree. Then if you go to the in order functions, everything is the same. You can see that the difference is that you call the in order traverse subtree the left subtree first, then visit the root node, then you traverse the in order to right subtree. So that means you are visiting root in between calling in order traverse with the left subtree and the in order traverse with the right subtree. That's why it's the in order, because you are visiting the root tree visiting the root in between using in between accessing left subtree and right subtree. Now that makes sense. What would be the post order? Post order is exactly all are the same thing, only order is different. So post order traverse the left subtree first, then post order the right subtree second, then you finally visit the root. So visiting root is the next one, so last one. So since there are three different so you are visiting left subtree first, then you are visiting right subtree. After visiting left and right, then you visit the root. That's why it's called a post order. So there are three different way you can traverse a tree. So let's see example. We'll see implementation in the next class, but we can see some traversing informations. So let's see visit these three using pre-order and post-order and in-order style. So let's try pre-order. So pre-order says that visiting root first, then left subtree, then uh, root, then left subtree, then right subtree. So if it is something like that, so 23 is a root. So we are visiting we start from the root. So 23 is the root, so we print 23. Then we go to the left side. After printing root, we go to the left side. So we found 19, and we found that 19 is a root, so we print 19. Then we go to the left side. After printing root, we have 12 over here, and we found that 12 is a root of this subtree. Then we print 12. Then we go to the left subtree. After printing root, we go to the 9. We go to this side, and this is a root of this other subtree, so root is a 9. Now of this subtree, you print root also, you print left subtree. Now you have to print the right. Since it doesn't have right, so you go to the next previous one. Now this 19 already printed, and left subtree whole thing is printed, 12 and 9 already printed. Now you print the right subtree, because you are done with the root and you're done with the left. Now you will done with the you have to do the 21. This is right. So you have done whole subtree, and you're done with the root also 23. Now you have to do with the right subtree. So you come to the right side, and when you come to the 33, you see that this is a root of this subtree, so you print 33 over here. Then after printing root, then you go to the left side, because the order is root, left, right. You go to the left side, then you print 29. Then after printing left side and root, then you go to the right side, then you have 54. So this is the pre-order. You are traversing something in that way: 23, 19, 12, 9, 21, 33, 29, 54. This is the pre-order way to traverse a tree. Now if you print, so say for example, now you try with the in orders. Okay, now is the try with the in order. So in order. So in order says that you print left first, then root, then right. Okay, so this is the way how to in order done. So left first, so you start with the 23. So this is not a left, so you go to the left side, and this is a root also, this subtree. This is not a left, so you go to the left side, and you also see that this is also root of some subtree. This is not a left, and you go to this side. And after coming this side, you see that left subtree is a null. So now you can print the root of this subtree, because left subtree of this subtree is null, so you can print root. So root is 9. Root is 9. So you're done with the left, you're done with the root. Then you need to do the right. Since right is a null, so you don't need to print anything. So now you go to this subtree. This subtree saying that you're done with the left side. Now you have to print the root. So the root is 12. So if you're done with the left side, if you're done with the right side, then you have to do with the right side. Left side and the root side, the root, then you have to done with the do with the right side. Since right side is a null, so you go back 19. In a 19, you see that you done with the left portions. Now you have to print the root. So root is a 19. Then you're done with the left, and you're done with the root. Then you have to do with the right. So right is a 21. So now you have done with the left of this node. Then you have to do with the root. So 23. So you have done with the left, and when you have done with the root, then you go to the right side. So when you come to the right side, then you see that this is a root. Then you go to the left side first. So after coming the left side, you see the 29, because there is no any left anymore, and there is no any right anymore. So you print 29. So when you're done with the 29, then you have to do with the root is a 33, and finally you have done with the left and you have done with the root. Then you go to the right side is a 54. So this is the in order style. Then you can see that the order of in order and order of pre-order is different. So in order basically saying that 9, 12, 19, 21, 23, 29, 33, 54. Now finally we have the post order. Post order saying that you have to done with the left first, then right first, then root. Okay. So you start with the 23 root. So what is the left first? This is so you see that this is the root. This is not a left. So you go to the left side, and you see that this is the root of these whole subtrees. This is not a left. So you go to the left side, and this is a root of this subtree. So you go to the left side, and you see that there is only left and there is only right. So you print 9. Then you go to the up back again. After coming 12, you see that there is no any right and you're done with the left, so you can print root now 12, because left, right, root. So left you already printed, right there is no any right, so you can print root now. So now you have seen you're done with the left side. Now you have to done with the right side before going to the root, because this is a post order. So you print 21, then you can print 19 root. So you see that you're done with the left side of this root. Now you have to done with the right side. So you come here, and you have coming here, you see that there is a left portion over here. So you go to the left side, then you print 29, then you print the right of this subtree is a 54, then you print the root of this subtree is a 33. Now you can see that you have done with the left subtree, then you have done with the right subtree, then you have to do the root finally. That is a 23. So you can see that post order, pre-order, in order, all are three different orders, and you traverse in that way. And this is the way how we can traverse a tree. You have to do practice to, because you will have this kind of exercise in your exams to print the data using pre-order, post-order, and in-order way. So you have to do practice these sort of things. In next slides, we'll try to implement this pre-order, post-order, and in order. How to implement those things, we'll see those things. Thank you very much.